Hello, my name is Amit Kumar and I'll be recording this demo lecture on the topic of Joule Kelvin coefficient or Joule Thomson coefficient. So let's get started. For this, let us consider a pipe which is insulated and is fitted with a mechanically operated valve. So this here is a pipe and this is a mechanically operated valve. We have insulated the pipe and valve so that no heat exchange takes place across the system. No heat is able to enter into system, no heat is able to exit out of the system, and this complete is we have taken it as our system. Now what we will do, we will place manometer and thermometers to measure the temperature and pressure. Where we will place it, we want to measure the temperature and pressure of the system upstream of the valve and downstream of the valve. Let's suppose this is a manometer which will give us the pressure upstream of the valve, and this is a thermometer which will give me the temperature. Likewise, I have placed a manometer which will give me a downstream pressure and thermometer to give a downstream temperature. So this here provides inlet pressure, this here provides inlet temperature, and this here provides outlet pressure, and this provides inlet outlet temperature. Now, so initially we have completely closed this valve so that if any flow comes from this side, it will reach up to this valve, and this valve will not allow the flow to reach go downstream of this it. Now we know we will fix the condition of pi and ti. What we have done is we have fixed the conditions here, pi and ti, of pressure and temperature. We have to fix the condition and the valve is completely closed at this moment. What we will do, we will rotate this valve by a small extent so that a small opening is created in this valve, and through that valve the gas can go downstream of this valve. And as the gas reaches downstream of this valve, we will measure the temperature and pressure. And let's suppose for this particular valve opening, the pressure value and temperature value came out to be P naught and T naught. Now we will alter the conditions by rotating this valve. We will rotate this valve again by small amount so that the opening becomes wider by a small amount, and through that the gas will escape out of this one, and new outlet conditions will be noted by this thermometer and manometer, which will be P naught and P dash and T dash, P naught dash and T naught dash. Likewise, we will rotate this, and again we will get P naught double dash and T naught double dash, and we can get different outlet conditions for this different amount of ball openings. Now all these points which we have obtained from different wall openings, these points represents the equilibrium state of some constant mass of gas, and we can plot these points on TP plane. This point on TP plane. So if I take up TP plane, suppose this is a TP plane, this is T and this is P, and on this TP plane, if we plot all these points, we will obtain a curve something like this. Now we need to know why this curve looks like this, what are the different points on this, and what is the significance of this curve when we are studying Joule Kelvin coefficient or Joule Kelvin coefficient, or how to calculate the Joule Kelvin coefficient. So the Joule Kelvin coefficient at any point on this curve is the slope of this curve. If you want to get the Joule Kelvin coefficient at any point of this curve, we just need to know the slope of this curve at that point, and we will get that Joule Kelvin coefficient. So how to get that? Let's get into the deeper side of this concept. So this curve is an isenthalpic curve. This curve is an isenthalpic curve, and why I am saying this is isenthalpic curve? So let's use steady flow energy equation, steady flow energy equation to the inlet and outlet conditions. So using steady flow energy equation, we know that the inlet enthalpy H1 plus inlet kinetic energy plus by 2000, this is just to make it in kilojoules, plus potential energy I'm just writing by PE, plus all the heat losses or heat gain will be equal to the outlet enthalpy. One here shows the inlet conditions and two here shows the outlet condition, plus outlet kinetic energy plus this is one outlet potential energy plus any work done, plus any work done. Now let's see what is happening here. So first thing is we have made the system insulated so that no heat transfer occurs across the system. So I can say that this is 0. So this is a horizontal system, as we can see, and so we can also neglect the potential energy. Now there will be a very small change in the kinetic energy of the system. There will be very small change in the velocity of the system of the gas as it goes across the wall. So we can also neglect the kinetic energy, and also for this system there is no work, no form of work done can be seen here. So what we get from steady flow equations are only two terms are left. That means H1 is equals to H2. H1 is equals to H2. This means that the enthalpy of the system is constant. Enthalpy of the system is constant. And what is to be kept in mind at this point is we have only fixed the inlet condition, but the valve opening is changing. So for fixed inlet condition and different valve openings, we are getting same enthalpy. So enthalpy of all these points, all these different points are same as to this one. And when we plot all these isenthalpic points, all these points having the same enthalpy on this TP plane, we get an isenthalpic curve. And the slope of this curve is the Joule Kelvin coefficient or Joule Thomson coefficient. So up to now we obtained this sort of curve on the TP plane for a fixed inlet conditions of Ti and Pi. Now what we do, if we alter the inlet conditions, from Pi and P1 and T1 to let some other conditions P2 and T2, so the inlet conditions are changed to some other value of P2 and T2. So this curve which we obtained was for P1 and T1 as inlet conditions. So for this curve the inlet conditions were P1 and T1. And if we do the same experiment for the inlet conditions of P2 and T2, we'll initially keep the valve at closed position and then we'll keep on opening it slowly. We'll again see that we'll obtain a similar kind of curve. But because the inlet conditions are different, so the enthalpy of this curve will be different. So it can't superimpose on this curve. It will take some other value of enthalpy and plot a isenthalpic curve. So this particular curve which we find is for inlet conditions of P2 and T2. Likewise, if I keep on changing the inlet conditions, we can get a family of these curves. Number of curves we can get. So for this particular curve, the value of enthalpy is constant, but for different curves, the value of enthalpy are different. And one thing which should be kept in mind, it is not a graph, it is not a curve of throttling process, because throttling, because of the friction, is irreversible process, and irreversible processes can't be plotted. So this is just a graph of point of equal enthalpy. This is just a curve of points of equal enthalpy. And mind you, so if this is, suppose this pressure is Pi and this pressure is Po, because of the friction, PO will always will be less than Pi. All outlet pressure will always be less than inlet pressure. But for temperature, we are not sure, and this is why we are calculating the Joule Kelvin coefficient, we want to know the variation in the temperature of the fluid with respect to variation in pressure. What happens when the pressure decreases, whether the temperature increase, decrease, or remain constant. We want to know that. Well, all these three things are possible. The temperature can be increased, the temperature can be decreased, or the temperature can remain constant depending upon the conditions. So let's explore those conditions, how to obtain that. Before going to the conditions, let us know about one more thing, inversion curve. So we can see one thing we can see is every curve has a maxima. Every curve, suppose this curve, the value keeps on increasing, and this here it reaches to maximum, then starts decreasing. So every curve has a shift of slope, we can say. Up to this point there is a positive slope, and then it becomes negative, and this point, at this point where maxima is reached, at this point the slope is 0 for this particular curve. Now suppose if we join all this curve having maxima, so it won't actually pass through this, but it's because of this. So if we join this maxima of all the curves, we obtain this curve, and this curve is very important. This is inversion curve. This is known as inversion curve. Okay, inversion curve is a curve which denotes all the maximum of the curves with different enthalpies, and the point on the curve, the point on a particular curve where the value of slope is 0 is known as the inversion point. This particular point is known as inversion point. This is also inversion point for this curve. This is also inversion point for this curve, and if we join all the inversion points, we get an inversion curve. Well, we'll see what is the significance of inversion curve in a few moments. So now let's find out a relation for the Joule Kelvin coefficient. So for that we will be using some thermodynamic equations. So first equation that I'll be using, we know this relation dH is equals to TdS plus VdP. This, I'm directly using this equation. I'm not going the proof of this equation. It's very easy. We are just using it directly. So dH is equals to TdS plus VdP. I need one more relation, and I'll use second TdS equation. So using second TdS equation, if I use second TdS equation, what second TdS equation says? It says TdS is equals to Cp dt, sorry, there will be minus T times curly V by curly T at constant pressure into dP. This is what second TdS equation say. So I've got two equations, 1 and 2, and if what I do is, if I put the value of this TdS in the equation 1, what I will get, I'll write here what I'm getting. I will get dH is equals to Cp dt minus T times curly V by curly T at constant pressure into dP plus V plus VdP. These are specific volumes. So this is equation 3rd. This is what is equation 3. Now we know that this throttling process is an isenthalpic process. We just proved it a bit ago. So we know that change in enthalpy will be 0, and if change in enthalpy is 0, we can bring this term to this side, and doing so what we will get is Cp dt is equals to T times curly V by curly T at constant pressure into dP plus V dP. Sorry, this is minus, and this is also, this will become negative if it comes to this side. Now what we will do, we will take dP common from both these terms. dP is common from in both these terms, and we will take dP common, and by doing so what we will get is we will just write Cp dt is equals to, will make this positive. So what we will obtain is T times curly V by curly T at constant pressure. So dp, sorry, this is my bad, minus V into dp. And we want to know the change in temperature with respect to change in pressure. So we will do some mathematical manipulations, and what we will get is dt by dp, which is also known as Joule Kelvin coefficient or Joule Thomson coefficient, which is denoted by mu j, and which will be equal to 1 by Cp T times curly V by curly T at constant pressure minus specific volume. So this is the mathematical expression to find Joule Thomson coefficient, or we can also say Joule Kelvin coefficient. Now let's now jump to the significance of that curves we find. Now here we can find out with respect to the change in pressure what will be the change in temperature. We can say from the Joule Kelvin coefficient. So how to calculate this from the curves? Suppose this is the TP plane, this is the TP plane, and on this TP plane this is a curve. This is a isenthalpic curve denoting any particular state, any particular inlet values for isenthalpic curve. This is the inversion point. Now we know during the throttling process the pressure decreases. So this point here, let's suppose this is our starting point, this is Pi in initial point, and a process, the gas undergoes throttling process, because of which the pressure will decrease. And if the pressure decreases, we'll get some other pressure somewhat here. Suppose this is PO, and if we join these 2 points, so see what actually is happening here. What actually is happening here is very interesting. Initially, for the inlet condition of Pi, what was the temperature? This was the temperature. This is temperature Ti. But when the gas undergoes throttling process, it reaches to position P0, and corresponding to P0, the value of temperature is this T0. And we can see from the graph T0 is greater than Ti. T0 is greater than Ti. That means if the gas is undergoing a constant constant enthalpy process, its temperature can rise. But can it decrease? Yes, it can decrease. And how it can decrease, we will see in this next graph. Suppose now we make another curve. This is again TP plane. On this plane, let us take another curve. Okay, this is the inversion point. This is the inversion point of the curve. And initially, let's suppose initially the point where we starting the throttling process, the pressure, inlet pressure, or we can say, is somewhat here. This is Pi. If this is Pi, this is the point, and the throttling process went up to this point. This is PO. So corresponding point on this curve is this one. And if we now find out the value of the temperatures corresponding to these points, so this is the inlet temperature and this is outlet temperature. And as can be seen from the graph, T outlet here is less than T inlet. T outlet is less than T inlet. It is completely opposite to what we got earlier. T outlet was greater than T inlet. So the temperature of the gas can increase or decrease depending upon the initial conditions. If the initial conditions are on the negative side, so if we look at this across this point, this portion of the slope, this portion of the curve is having negative slope, and this portion of the curve is having positive slope. This we can see this portion of the curve is no, actually this is not like this. I'm not this is somewhat if we take a small portion of this, and if we do some mathematical calculations, then we can find this is negative slope. So this point of the curve is having negative slope, and this point of the curve is having positive slope. So if the initial conditions are on the negative slope side, and the throttling, for the throttling process, the value of temperature will increase, and on the other side, if the initial conditions are on the positive side of the slope, the value of temperature will decrease. But this is not always the case. Suppose, let us take another condition where the inlet conditions are at somewhat this point, and P inlet dash, I'll name it P inlet dash, and if the throttling takes up to this point, P outlet dash. So this is the inlet pressure, this is the outlet pressure. So the corresponding points here are this and this. Now if we join these 2 points, we find out that the inlet temperature is exactly equal to the outlet temperature. So the inlet temperature can also be equal to the outlet temperature, irrespective of whether it was on the negative side, slope side of the inversion curve, or positive slope side of the inversion curve. But the value of throttling that has to be done is on the very higher side. So this is the concept of Joule Thomson coefficient or Joule Kelvin coefficient. Hope you like the video, and thank you.